Hello, this is Kate from Lamina, chemical reactor manufacturer for graphene and graphene oxide. Today, I'm going to introduce the continuous process technology using Taylor flow for graphene and graphene oxide. My presentation will be covering what the Taylor reactor is, advantages that the Taylor reactor brings, application with the Taylor reactor, products, and the brief company introduction. For the graphene production, there are two main categories, top-down and bottom-up manufacturing techniques. Under the top-down manufacturing techniques, there are dry exfoliation, like Scotch tape, liquid phase exfoliation, chemical reduction of graphene oxide based on Homas method, and electrochemical exfoliation. Bottom-up manufacturing techniques, there are direct chemical synthesis, epitaxial growth, plasma-based methods, and CVD. These graphene production processes keep changing for the process improvement. The most mentioned challenges are scalability, number of layers, structure damage, size, quality, operation condition, and cost. However, the Taylor reactor based on the liquid phase exfoliation can meet all these requirements. So first, you don't need to worry about the scalability. Since we have a wide range of working volume reactors, you can produce just a liter of graphene for your R&D, but also large quantities for the mass production. Of course, the production rate varies per meters, but about 2062 tons can be produced yearly. Several publications reported the Taylor reactor can produce the single and few layer graphene without any defects. Also, it is easy to control the size by the agitation speed and exfoliate the uniform graphenes. Our Taylor reactor runs at the room temperature, not at the high temperature or under the vacuum condition. Lastly, the production cost can be significantly saved, as the Taylor reactor not only shortens the reaction time but also saves the water consumption for rinse. What makes this possible? The answer is Taylor flow. For flow, there are lamina and turbulence flow. As you can see the picture of candle, the lamina is straightforward flow without being disturbed. Turbulence is irregular flow like waves, rivers, and clouds. Lamina flow is not used in the reactor because it has no mixing power. So turbulence is used for conventional reactors such as batch and PFR. However, because of the use of irregular flows, the materials are randomly mixed and reacted, resulting in a bad results. However, our Taylor reactor is utilizing the Taylor flow, which is the transit area between lamina and turbulence. As you can see the picture in the middle, the Taylor flow is mixing particles homogeneously within the Taylor vertices and brings high reproducibility. So our Taylor reactor is easy to scale up thanks to toroidal vertices. The flow created when the fluid flows in the gap between two different cylinders, both with the same center, and the inner cylinder rotates at the constant speed, is called Taylor flow. The fluid close to the inner cylinder tends to move toward the stationary outer cylinder due to the centrifugal and Coriolis forces created when the inner cylinder rotates. The fluid gets unstable, and then a pair of rings rotating in the opposite direction each other is created along the axial direction. As shown in the upper right side of this slide, one ring moves in the clockwise direction, but another ring moves in the anti-clockwise direction. This one ring pair is defined as one Taylor flow. The formula for the number of Taylor is as shown below. As the first Taylor reactor manufacturer in the world, we designed the reactor to meet your needs with no house. The CFD, the left side of the picture, shows the creation of the Taylor flow. Since the Taylor flow is quite invisible, CFD is the proper tool to see the Taylor flow. As you can see the CFD data, the Taylor flow is created with the 8 seconds and gets stabilized. The number of the Taylor flow depends on the agitation speed. So the Taylor flow can be created more than 2.7 RPM, and when it's over 1000 RPM, you can see some turbulence between Taylor flow. When it's over 5000 RPM, the Taylor flow disappears and it turns to the turbulence. Having said, the materials are reacted within each Taylor vertex, and Taylor vertices are not mixed each other. Let's see the short video recorded in our laboratory. It shows the different colors based on pH values. So if pH values are less than 12, it's blue, but more than 12, then it's pink. So once the particles are formed, the vortices are not mixed each other, and the particles are moved to the side at the speed of the flow rate of the pump. So as soon as the solution are injected, you can see it is not mixed at the end and randomly. It moves sideways along the regular Taylor flow. The structure of the Taylor reactor is shown here. So number 1 is the feeding port, where the materials are injected. Number 8 is the reaction zone, where the injected materials are mixed. And number 5 is the reactant outlet, where the reactants are discharged after the reaction. Since it has the double jacket structure, number 7 is the temperature control zone. Number 3 is inlet, where the temperature control media is injected. And number 2 is the outlet, where the media is discharged. Number 4 is drain, used for cleaning. And just for your clear understanding of the structure, the black one is rotating in a cylinder, and the blue is doubled out outer cylinder. The reaction zone is the gap between the inner and outer cylinders, and temperature control zone in the red area covers the reaction zone in yellow. You might think we discovered the Taylor flow, but it is not. In 1900, Kuwait found the Taylor flow between lamina and turbulence. In 1950, Taylor made equation for the creation of Taylor flow. Based on the equation, we design and manufacture the Taylor reactor for the first time in the world. Our reactor has been used not only here in Korea, but also many countries such as US, Europe, Japan, and China for the purpose of the new material research and development and also mass production. From now on, I'm going to show you the advantages when the Taylor reactor is used for the production of graphene and graphene oxide. First of all, the Taylor reactor can not only reduce the reaction time, but also get the high yield. Let's see some excerpts from one of the papers. The publication shows XR dependence of oxidized graphite prepared by the Taylor reactor, and Hummus method with the tank reactor. Even for the reaction time of 60 minutes, the sample prepared by Hummus method showed the two XRD peaks, indicating that the significant amount of non-oxidized graphite flakes was still in the samples. However, the sample prepared using the Taylor reactor no longer showed the characteristic peak of graphite after 30 minutes. Therefore, this XRD research shows the oxidation of graphite flakes into graphite oxide can be achieved in a significantly shortened reaction time by the Taylor reactor. The bar graph in the right side shows the comparison with the recovery rates of graphene oxide prepared by the Hummus and Taylor reactor. In case of Hummus method, recovery rate was 37% with a reaction time of 60 minutes, indicating that more than 60% of under-oxidized graphite particles were present in the products. However, with the Taylor reactor, the recovery rate was increased to 93%. So this result confirms the use of the Taylor reactor is efficient oxidation method from graphite into highly oxidized graphite oxide in a significantly shortened reaction time. Here is another paper for graphene oxide. After 60-minute reaction time, the recovery rate of graphene oxide prepared by the Taylor reactor is around the 98%. However, the recovery rate of Hummus method is only 34%. If the recovery rate of Hummus method becomes comparable to that of the Taylor reactor, 1,440 minutes, which is 24 hours, is needed. However, as shown in the right side of the graph, the viscosity goes extremely up to 10 kcp, making it hard to filtrate it. Second advantage is high quality. One paper characterized the quality of exfoliate graphene flakes by Raman and XPS. Raman's spectrum of thin film produced from graphene dispersion shows a relatively weak dip band, indicating a low degree of defect. Considering that the Raman laser beam spot size is larger than most of the graphene flake size, the observed dip band was likely to be dominated by the edge rather than base plane defect. So base plane defect was likely introduced during the high shear exfoliation of graphite by the Taylor reactor. And given that undamaged base plane were confirmed, the small peaks in the XPX spectrum may come from the residue solvent like MMP within the thin film of graphene flakes. Therefore, XPS shows no evidence of oxidation, suggesting the high quality of the graphene flakes produced by high shear exfoliation of graphite. Also, another paper shows the TEM images of exfoliating and functionalizing graphene, MOS2, and boron nitride. As shown in TEM images, hexagonal structures were observed in the sheet, which strongly suggests that the original base plane were not damaged during the exfoliation process by the Taylor reactor. So as a result of all this data, you can produce the high quality products with our Taylor reactor. The third advantage is it's easy to control the size. So by controlling the agitation speed and reaction time, the size can be easily controlled. One paper showed the tendency. Also, in the same publication, the author also compared the letter size among sonicator, homogenizer, and tailor reactor. The height profiles reveal uniform flake thickness of 0.75 nanometer, which is the typical of the exfoliated individual graphene oxide sheet. However, the letter size shows some size variations. 5 micrometer for sonicator, 20 micrometer for homogenizer, and 50 micrometer for tailor reactor. The next advantage is the tailor reactor can save water consumption and also recycle the sulfuric acid. So as mentioned previously, since the viscosity of the reactant mixture produced by the tailor reactor is relatively low, the oxidized graphite slurries were successfully separated into sulfuric acid and graphite oxide. As we all know, the amount of water consumption during the graphene oxide synthesis accounts for the large portion of the production cost. So compared to the Hamas method, after filtrating the sulfuric acid, the remaining graphite oxide slurries can then be washed with the significantly reduced amount of water by 75%. Also, the filtrated sulfuric acid could be recycled for the repetitive graphene oxide synthesis in the tailor reactor. So in the following, various types of graphene oxide products, like graphene oxide with the fresh sulfuric acid, one-time recycled sulfuric acid, and two-time recycled sulfuric acid, were analyzed and shown here in this slide. All this data suggests that the high-quality single and few-layer graphene oxide can be successfully produced even with the recycled sulfuric acid during the synthesis process, resulting in saving a lot of production costs. Lastly, it is easy to scale up. Tailor vortex consists of a pair of two rings with 1:3 ratio. As we all saw the video, each vortex is not mixed each other, and the particles are micro-mixed within the Taylor vortex. So therefore, you can consider its Taylor vortex behaves as a one-tank reactor. So let's assume there are the same working volume tank type reactor and Taylor reactor, which is the 1K liter. And the number of the Taylor is 14 with the Taylor reactor. So even though the working volume of the Taylor reactor is 1K liter, it can be considered as 14 of 71 liter tank reactors. So when we can compare the ease of scalability between tank reactor and Taylor reactor with the same working volume of 1000 liter, we all know it is much easier to scale up to 71 liter than 1000 liter from 1 liter. Therefore, comparing to the conventional tank reactor, anyone can easily scale up with our Taylor reactor. As a manufacturer of reactor, we are quite not sure how graphene and graphene oxide produced by our Taylor reactor can be applied in detail. However, I'd like to show you some extracts showing the materials made by our Taylor reactor can be used for various applications. First, functionalization. One paper showed how to functionalize the graphene oxide sheet with the nanoparticles. Metal salt aqueous solution was introduced in the reactor in the course of oxidation reaction of graphite flakes. Subsequently, the metal oxide nanoparticle nucleated and grew on the graphene oxide surfaces, resulting in graphene oxide sheets decorated with the 10 nanosized Fe3O4 nanoparticles. Another paper showed the application for energy storage film and reported its electrochemical performances. In the very left side, all the CV curves exhibited a rectangular shape, which indicates ideal capacitive behavior. Also, when the current density was increased from 0.5 ampere per gram to 15, 94.3% of the initial capacity was retained, suggesting the films has good rate capability. And lastly, the graphene films exhibited no capacitance losses even after 5K cycles under the current density of 2 ampere per gram, which is 99.2% retention. In the same publication, the author performed inkjet printing using nanosheets dispersed in the water. Using the inkjet printer with the prepared inks, the author was able to print letters K, N, and U, and surface SEM images of letter revealed uniform patterns of the nanoparticles. It probably caused by the effective dispersing and wet capabilities. This high electrical conductivity allowed the author to print electrical circuits that was able to power a LED. It suggests the low amount of defects in the sheet. Through the excerpts, we are able to confirm there are some applications with the materials prepared by the Taylor reactor. However, not limited to the data that I was showing, I'm sure the materials can be used in more fields. Our model for graphene and graphene oxide can be divided into 4 categories, and you can refer to the production rate per day. Production volume actually depends on the residence time and solid content, but was calculated under the condition described in this slide. First, we have the LCT Lab 2 model, which working volume is 100 milliliter or 200 milliliters. It can produce about 0.024 kilograms per day. Next, we have LCTR Terra, which working volume is 1 liter, and it can produce about 0.24 kilograms per day. And we have the LCTR Peta, which working volume is from 5 liter to 50 liter as a viable scale reactor, and it can produce 12 kilograms per day. And lastly, we have LCTR EXA model, which working volume is from 100 liter to 1000 liter as an industrial scale reactor. About 240 kilograms per day can be produced, and larger than 1000 liter working volume reactors can be manufactured upon the request, and the design up to 10K liter are available. We also provide all setups for lab scale, like chillers and then pump, and also industrial scale too. So we can also produce you turnkey solution from the pre-mixing to dryer. So we Lamina are based in South Korea and founded in 2010. We designed and commercialized the Taylor chemical reactor for the first time in the world. We hold 20 patents worldwide and apply 1 to 2 patents annually to protect our technology. Also, all products models are CE certified, and we have our own R&D center for testing. Lastly, we have worldwide distribution partners too. It was all about our technology and products, and thank you very much for watching this video. Please feel free to reach out to us by email shown above if you have any questions or requests about the graphene and graphene oxide process. We can also conduct some sample tests in our laboratory, so please do not hesitate to contact us. Thank you very much.